So this section is kind of a review of all substitution and trig, some trig integrals and stuff like that. So I just want to basically do a couple examples. These can be tough. Like that's I'm not going to sugarcoat that. These can be tough because it's not always easy to see, the tricks. Sometimes there are some algebra tricks you have to do before you can figure out the integral. But I just wanted to do a couple that I thought were a little bit more challenging. And then that might help you kind of see my process of how to do that and some ideas on where we could go with this. So let's look at one like this. So you should have copied down, there was that table with some of the basic integration formulas that you need to know. So that's something that you should copy down, make sure you know those formulas. Look in the module, it tells you, what numbers that you need to know and what numbers will be given on the test. But let's look at something like this. So I have the integral from 0 to 1 of t squared over 1 plus t to the 6th. Now there's some things I could do. So, so if I don't see that this is a direct derivative of any function that I know. I could, what if I let u equal 1 plus t to the 6th, that might be an option, but then the derivative, if you notice the derivative of that though, is 6t to the 5th dt, which isn't always a horrible thing, but I have this t squared right here. So, I could get rid of 2 of the t's from this t to the 5th, but I'd be left with t cubed, and then I don't have any other t cubes anywhere. So I don't think that's going to work to let u be that. Please understand also that sometimes you don't always get the right method right away, and that's okay to try things that are different, okay? Try things that maybe don't work, try stuff. That's one thing about becoming good at math, is you can't be scared to maybe take a chance and maybe not get it right exactly the first time, okay? What I do know is I know that the integral of 1 over 1 plus x squared dx, whoa, I don't know what I did just there. I'm gonna give myself a little bit more room. So the integral of 1 over 1 plus x squared dx, right, is tangent inverse. That's one that you're gonna want to know for sure from memory. So with that in mind, I'm going to kind of look at this and see if there's something else I could do. So for example, if I redo this from 0 to 1, I still have t squared. Could I make this look like 1 plus something squared on the bottom? Well, I could. T to the 6th is really just t cubed squared, right? Because we multiply exponents when I raise an exponent to an exponent. Once I have done that, now, oh, whoops, sorry about that. Now I can see that I could do a u substitution. I could let u equal t cubed, and then notice I'm going to get something that looks like this, which is what I want, okay? So let's go ahead and do that. Again, this takes time to see these. You've got to practice them. You have to try different things. So what is du? du is 3t squared dt. Guys, these dt's are important. You need to write those. Now it's a definite integral, so when t is 0, right, it looks like u is 0. And when t is 1, that's kind of nice. U is 1, it looks like. That's great, with the relationship of u equaling t cubed. So now I'm going 0 to 1 still. What do I need to get rid of here? I know I'm going to have a 1/3 du, right? Is that t squared dt? So I get 1 over 1 plus u squared times 1/3 du, and we're ready to go. This is good stuff. So I get 1/3. The antiderivative of 1 plus u squared is going to be tangent inverse of u evaluated from 0 to 1. So this is 1/3 tangent inverse of 1 minus 1/3 tangent inverse of 0. So let's talk about this tangent inverse in case you haven't done it in a while. Remember, tangent inverse, its range. Tangent inverse spits out angles in either 1 or 4, okay, or between negative pi over 2 and pi over 2. So what this is asking is what angle, when I take the tangent of it, gives me 1 that either is in quadrant 1 or quadrant 4. And that's going to be pi over 4, right, because it's positive, and tangent is positive in the first quadrant. I don't know why I put pi over 3. I meant to put pi over 12 because it's pi over 4. This whole thing right here is pi over 4 times 1/3, so that's pi over 12. And then for tangent inverse of 0, what angle when I take the tangent of it gives me 0? Between negative pi over 2 and pi over 2, that would be 0. So my final answer for this one is pi over 12. So again, just one to kind of think about something like this to try, because it's gonna be kind of hard sometimes. Let's do another one really quick. Again, I'm just kind of doing some examples that I think look kind of interesting. How about one like this? Now, I actually have not done this one. So what I kind of want to do this because I want to show you my thought process for it. I hope I can do it. I'm sure I can. It'll be fine. So when I look at this, my gut reaction here is to try and do u substitution with u equaling 1 plus e to the x. I don't want to try and like FOIL that out to the 9th or anything like that, but I'm going to just try something. So let's see what's going to happen. If I let u equal 1 plus e to the x, right, then I have du is e to the x dx. This is really good because then this guy replaces that, right? And then this 1 over e to the x is going to be replaced with u, so we're set there. What else do we have to get rid of, though? We have 1 minus e to the x here. Well, what I could do is I could actually solve this equation right here for e to the x. So let's see what e to the x is going to equal here. E to the x, if I solve for e to the x, would equal, whoa, I don't know how I did that. That was cool, though. Would equal u minus 1. So I'm actually that's what I'm going to do for a substitution. I'm actually going to take this e to the x right here, and I'm going to substitute it with u minus 1, and I think some cool stuff's going to happen. So try stuff, right? Let's see what happens now. All right, what does this integral become? All right, so that's going to be u to the 9th, right? The purple. The orange is going to be replaced with the du, right? So we're going to be good there. And then what do I have here? I'm going to have 1 minus u minus 1. Parentheses are important. And then again, that e to the x dx is du. Now I think we're going to be able to do this. Let's see what happens here. So I have u to the 9th. I'm here, I get 1 minus u plus 1. So that's 2 minus u du. And now how do I integrate this? Well, I'm going to just take the u to the 9th through so that I can use the power rule. Oh, whoops, sorry, excuse me. That should be in the 9. U to the 10th du, isn't that cool? These are kind of fun. I like them because they're puzzles you have to solve. So I get 2 over 10 u to the 10th. Now I'm ready to just use the power rule. Minus 1/11th u to the 11th plus c. And then what was my original u? If we look up here, my original u was 1 plus e to the x. So 2 over 10, don't leave it like that. That's 1/5. 1 plus e to the x, e to the x plus 1, it doesn't matter. Minus 1/11th, 1 plus e to the x to the 11th, all plus c. Cool. I like it. Great. Let's do another one. I'd like to do one maybe where we're dealing with some trig, because don't we just all love a little bit of trigonometry? I know, I do too. I agree. So let's look at something like this. Sine of x plus 1 all over cosine of x dx. So this one can look a little bit tricky because maybe you're not sure, really what to do with this. You may not, let me just say that again. I haven't even said it yet. You may not just go along your happy way and take the antiderivative of all these three things and divide it by each other. You cannot distribute integration over multiplication and division. Okay, so don't do it. Just please don't do it. Don't do it, guys. Please don't do it. Whoops. Sorry about that. All right. So let's see what we should do. So I have the sine of x plus 1 all over cosine, and what I would do with this is split it up, especially if you have a fraction and you can't see, well, I guess, yeah, here's the problem. Let me show you a mistake that I see a lot. I see a lot of people say, well, I'm going to let u equal sine of x plus 1, and then I'm going to let du is cosine x dx, and oh, look, I have a cosine, so that'll work. Actually, you don't have a cosine. You have a 1 over cosine, which is different than cosine. So that substitution wouldn't work. I could try and let u equal cosine, and its derivative is sine, but I have a sine plus 1. I don't just have a sine. So we have to do a little bit more here. And what I would do here is split these up. That's a good trick to use. If you have one term in the denominator, you can't split it up if you have, you know, the addition or subtraction in the denominator, but I can split it up if I just have a single term in the denominator and two terms in the numerator. So now let's see what this is going to be. So I have the integral of the tangent of x, right, plus secant of x dx, okay? Integral of tangent of x is one that I will give you on, you can actually, that one's not hard to do. If you were just integrating this, you would just let u equal cosine of x, and then du is negative sine x dx, okay? And so you'll be off by a negative, but it's okay. So if you look at the book, right, we know that the integral of the tangent of ax dx is equal to 1 over a natural log absolute value secant of ax plus c. Okay, so that's and you can get there from this. I'm not going to prove it for you. You're welcome to look that up. I think it's example 1 in your book. You can look that up on how to do that. And then the other integral we're going to need is secant x. And that one is actually pretty fun to prove. But just for time's sake, I don't think we're going to do that. And let me put the a in there because that a, that's where that 1 over a comes from. It comes from dealing with the chain rule, right? So if you have like secant of 5x, you'd have to divide by 5 to take care of the chain rule. So the antiderivative of secant of ax is 1 over a natural log of secant ax plus tangent of ax, absolute value of those. That's important. The absolute value is important. All plus c. Both of those are proven in your book in example 1 and example 2, and they're kind of cool to look through. I understand your definition of cool and my definition of cool are different, but I encourage you to look at it. It's actually pretty interesting. So I'm just going to go ahead and use those. Again, those are type of ones that'll be given on the test. But what is a in this case? A is just 1. So the integral of tangent will just be the natural log of secant. Okay, and then the integral of secant will be this natural log of secant plus tangent. Let me get rid of this stuff. No, man, I'm sorry. I keep going to my internet browser. So plus natural log of secant x plus tangent x, all absolute value plus c. And you know, there's not a lot I can really do with that. If I really wanted to, I could like addition of natural logs becomes multiplication with a single logarithm, but I think we'll just let it go there and be happy with what we got, right? Good. All right, like 2 more examples. I want to show you one where you have to complete the square and then one where we have to divide 2 fractions, because that one can be a little bit tricky. So let's actually do one with division first. So quick example. Oh, this one's a doozy, but let's do it. It looks like fun. Negative x to the 5th minus x to the 4th minus 2x cubed plus 4x plus 3. Oh my goodness, all over x squared plus x plus 1. I think this one's going to be a bit tricky. I think we're going to get a lot of stuff going on here, but it'll be actually pretty fun because I think we're going to have a completing the square. Again, I haven't actually done this one. I think we're going to have a completing the square plus a long division, which just right there is a good time. All right, so this you're going to want to do long division. So there's again, you may not take the antiderivative of the numerator and then the antiderivative of the denominator and just divide them. You cannot do that, okay? So this is what we call I hate that they say improper, but it's an improper fraction because the degree of the numerator is bigger than the degree of the denominator, meaning we could divide this. So let's kind of remind ourselves, whoa, sorry about that. kind of remind ourselves about long division of polynomials. So the way we do long division of polynomials, if you don't remember, and some of you might have, you know, the synthetic division, which you are welcome to use that. I'm just going to do the good old-fashioned division of the polynomials. I wasn't taught that synthetic, and I've never had to teach it, and so I just do the good old regular stuff. So what we're going to do, just like when we divide regular numbers, I want to look at what times x squared would give me negative x to the fifth. Well, a negative x cubed would do that. I'm going to put that over the x cubed here. And then you're going to take that x cubed and you're going to multiply it through times each one of these. Whoa, sorry, that was my book just slamming into my desk. All right, so I'm going to take that and I'm going to multiply it through to each one of those and then bring it underneath, just like we would for regular good old division of numbers, right? So I get x to the fifth, I'd have minus x to the fourth, and then minus x cubed. And then remember, we subtract them. And I always put parentheses so that I remember that I am subtracting, right? So I have to take that negative sign through to everything. So that becomes a plus, 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 plus. All right, so what do we get? That's 0. That's why we did it. That should happen. Oh, that's nice. Those go to 0. And then over here, we just get a negative x cubed, and then bring everything down and keep going. Okay, so what times x squared gives me a negative x cubed? I would need a negative x. So negative x times this whole thing right here. Let's do that. We get a negative x cubed minus x squared. Oh, I don't have a squared. So if you don't have a squared, what you might do is kind of, excuse me, give yourself a squared. We don't have any squareds, but it helps kind of organize it a little bit. So I have minus x squared and then minus x. So then you can kind of see. And again, I'm subtracting those, so that actually becomes all plus. Those cancel. That's why you did it. This gives me just a 1x squared. This gives me 5x. And then I have a plus 3. I'm going to go back up here and give me the well, that's all right. I was going to put in the 0, but I don't need to do that. So, all right. And then finally, x squared. What times x squared gives me x squared? Well, that would just be 1. Or how many times does x squared go into x squared? 1 time. So I'm going to take 1 times x squared plus x plus 1. So I get x squared plus x plus 1. And then I'm going to subtract that whole thing. Okay. So if I subtract that, that's 0. That's why we did it. Here I get 4x, right? And if I subtract that, I get plus 2. Okay. So you did all of that, and what that says then is that this whole thing right here, I don't want to rewrite it because I'm lazy, but this whole thing right here, guess what that equals? It equals this plus the remainder divided by the divisor, right? So if I had like 10 divided by 3. 3 goes into 10 3 times 9, and I subtract, I get 1. So this would be 3 and plus, right? I shouldn't have used 3. 1 over 3, where this 3 right here is the divisor that corresponds to this. So it's going to be the same thing for this kind of horrific fraction that we had. I'm going to take what I got my division to be, that negative x cubed minus x plus 1, and then I add the 4x plus 2 all over the x squared plus x plus 1, and then all of this dx. And now we got to figure out how to integrate this. So that whole thing was just so that we could maybe integrate this. So let's go ahead and do the easy stuff. I know I can integrate this pretty easily. That's a negative 1/4 x to the fourth minus 1/2 x squared plus x, right? So that I was able to integrate pretty easily. This guy, I thought we were going to maybe have to complete the square, but I don't think we're going to have to. Let me show you. I mean, you always want to go to like a u substitution before you get going too crazy for anything else. And I think we can use u substitution here. So let's see if we can do this. If I let u equal x squared plus x plus 1, that's really my only option, right? What is my du? It's 2x plus 1 dx. But notice, if I factored out a 2 from this, do you see how I'm going to get that 2x plus 1? Isn't that cool? So I actually have the derivative of the bottom sitting there, and I can replace that with du. I'll just be left with that 2 right there, but that's okay. And then I'm going to have 1 over u. That's really, really cool. So, so let's do that. So I'm going to be left with the integral of 2 over u du from that u substitution. That worked out lovely. I'm going to rewrite this. I'm not going to be lazy. I'm going to make sure when I put an equal sign that I do, in fact, have two things that are equal. Antiderivative, so this is 2 times 1 over u, right? Antiderivative of u is natural log absolute value of u, and then I have a plus c added on to all of that, and then my final answer, I know I have to write all of this again. That's okay. That's part of mathematics, is being precise. 2 natural log absolute value of x squared plus x plus 1. I believe that's always positive. So you probably don't have to have those absolute values, but it doesn't hurt to have them. Oh my goodness. Wow, that was a lot. I need a nap after that. That was a big one. So, I mean, that one was a bit extreme to show you the division. Wow, I don't know what I just did with that. But I hope it kind of makes sense what we did. All right, you guys, one more example with completing the square, and then we'll call it good. So this one's going to be a pretty simple one. But completing, you can kind of forget about completing this square sometimes. All right, so let's look at one like this, and we'll call it good. All right, so for something like this, if I'm looking at this, you know, I can't really do substitution. The only really possible choice for that would be if I let u equal x squared minus 2x plus 10. Its derivative is 2x minus 2, so I clearly don't have anything there to deal with that. So there's not much I can do. Here's what I do know, though. I do know one, and this would work too. Look at the fun sheet. There's one like this where it's dealing with sine inverse. But I do know that if I have dx all over a squared plus x squared, that's basically 1 plus x squared. So if I have an a there, then I basically have tangent inverse, okay? So this right here is the antiderivative. 1 over a squared plus x squared is the antiderivative of 1 over a tangent inverse of ax plus c. That one you got to know. So what I'm hoping to do is I'm hoping to manipulate this denominator right here. So basically that I get a sum of squares. I don't even care really what's happening inside here or here. I just want to see if I can manipulate this somehow to get a sum of squares. And the way I can do this is by the method completing the square. So I'm going to show you how to complete the square. So completing the square, and you probably remember this from algebra, is you take half of the middle term. Half of the middle term is -1. Then you square it and add it in. So -1 squared is 1. But because you brought in that 1, you have to also take it away, right? We can't just bring in a 1 and say it's the same polynomial. So this is a trick mathematicians use a lot, is they add something and then immediately take it away. Because look at this, it's still the same polynomial, right? The ones would cancel, I would still get the same polynomial. But why did we do that? Because now if you notice, these 3 right here make a perfect square. This is x minus 1 times x minus 1, or x minus 1 squared. 10 minus 1 is 9. So now look at why we did that. So now my integral dx over x squared minus 2x plus 10, right, is going to become the integral of dx over x minus 1 squared plus 9. Now watch what I can do. So if I let u equal x minus 1, then notice du is the same as dx. So now what do I have? I'll put the 9 first, just to make ourselves feel better. I have 9 to make it look the same kind of as what our formula says. I have an a squared plus x squared basically, right? So if I look up here at this guy, I see that in this case, what is a? A is 3, and what is x? X is u. So by doing that, by completing the square and finding that, I know then that this is going to be 1/3 tangent inverse of u plus c. Okay, and then what is u? Well, my u, I'm going to come back here and find my u. So what is my final answer? 1/3 tangent inverse of x minus 1 plus c. And we're done. Isn't that great? I love that one. Okay, guys, 24 minutes. I know that's a long, a lot of examples, but these are tricky. I know I've said this before, I'm sure, but you just got to do them. You guys sit down, you got to do all the suggested problems. You have to do the fun sheet. You have to practice, 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 so that when you get to an exam situation, you're going to be able to see kind of what is happening. And because that's all, this whole chapter is integration techniques. So we're just going to be integrating, integrating, integrating. Let me know if you have any questions.